Good afternoon friends. Today we shall be taking up Fourier series. So far we have discussed about network functions and their behavior under different conditions with the different types of excitation, for example a ramp or a step or an impulse or a sinusoid. Like this, we have taken up different types of functions and we have seen the behavior of networks, and we have used so far in the time domain the response has been evaluated by using Laplace transform. Okay. Suppose you are given a network and you have a periodic function. Then you take the Laplace transform of this, take the network function, and then you can evaluate the response. So the response will also be periodic or something like this. Now the response that we get taking Laplace transform of the function is giving me a total solution, that is, say total solution means including the transients. Suppose the response is like this. After some time it will be stabilizing to a steady value. If you are interested in getting the steady state solution, we are not interested in the transient part, we are interested only in the steady state solution. Then there is an advantage of using the frequency response technique. We have studied so far the response due to a particular frequency. Okay. Now if you are giving a periodic function, I would say of this type, if you are giving a periodic function as input, is it possible to resolve this into large number of sinusoidal functions? Our aim here is to resolve that and then find out the response corresponding to each elementary component of those functions, sinusoidal functions, and the response due to each one of them you calculate independently, then use superposition theorem, take the total sum, that will be the response due to any periodic function. So for periodic power signals, we mean power signal means signals with finite average power. So with power signals, this resolution results in Fourier series. That is, the function which is periodic has some average power, finite average power, and that can be decomposed into a Fourier series. If it is continuing, if it is an energy signal, that is finite energy but it is not periodic, then we resolve this by Fourier transform. So for periodic function, of finite average power, we go for Fourier series, and for energy signals, that is aperiodic signal with finite energy, we go for Fourier transform. Now before we start resolving the periodic signal into Fourier series, let us see some basic fundamental principles, fundamental properties of orthogonal functions. What are orthogonal functions? Orthogonal functions are set of functions, say I call it phi t. it is a set phi 1 t, phi 2 t and so on. Phi 1 t, phi 2 t and so on. Then this function phi j t, phi I t dt over a range L should be equal to 0 for I not equal to j and is equal to some constant for I equal to j. Okay. If the function set phi, the members of that function set obey this particular equation, then it is an orthogonal set. If k is equal to 1, then we call it orthonormal set. Okay. Now, any orthogonal function can be scaled to an orthonormal set. If I divide phi I by root k, define it as some phi I dashed, then phi dashed set, which will be phi 1 dashed, phi 2 dashed and so on, this will be an orthonormal set, because when I take the product it will become root k into root k. So, that will give me k. So, the end product will be 1. Now, let us use this in our analysis of Fourier series. Any function, say v t, call it, which is periodic, v t is v t plus minus k t, capital T is the period, then we are resolving v t as a trigonometric series a 0 plus a 1 cosine omega naught t plus a 2 cosine twice omega naught t and so on, plus b 1 sine omega naught t plus b 2 sine 2 omega naught t and so on. Okay. Now, let us see this sine and cosine function set. Sine omega naught t, for example, into sine say 3 omega naught t. If I integrate over the period t, t is the period corresponding to 2 pi by omega naught. Okay. So, over this period t, if you integrate this, it will turn out to be 0. You take any function, okay, like phi 1 t, phi 2 t, two different functions, you will find sine omega naught t into cosine 5 omega naught t, say, that will also be equal to 0 over one period. Sine omega naught t into sine omega naught t, if you integrate, which is sine squared, it will turn out to be t by 2. You can work it out yourself. Similarly, you take sine 5 omega naught t into sine 5 omega naught t, that will also give you t by 2. So, the set phi whose members are sine omega naught t, sine 2 omega naught t, sine 3 omega naught t and so on, and cosine omega naught t, cosine 2 omega naught t, etc. They are all members of this orthogonal set. Okay. We shall be using this property in resolving these values. Before we start resolving this, let us come to a simple example. Let us have Vt equal to sine omega naught t. Let us take just a trigonometric series, sine 3 omega naught t, sine 3 omega naught t into 1/3 plus 1 by 5 sine 5 omega naught t, and so on. Let us take a series like this. Let us take only part of this function and gradually increase the number of terms. V2t is sine omega naught t plus the second term. V3t is again the third term added, and so on. They are all called harmonics of omega naught, 3 omega naught t, 5 omega naught t. So, that means they have a time period which are integral frequencies are integral multiples of the fundamental frequency. This is called the fundamental frequency, or integral submultiples of the time periods are integral submultiples of the original time period. What will be sine omega naught t like? The first function. The first function looks like this. Okay. Then the second function, when I add like this, the third function, to avoid jumbling up, I will show here separately. Like this. So, you can see there are 3 humps, there are 2 humps here when I am taking the second term, when I am taking the third term there are 3 humps, and so on. Okay. So, as you keep on increasing this gradually approximates to a function like this. And finally, it will tend to, when I take it up to infinity, it will tend to a rectangular function. That means, as you keep on increasing the number of terms, this gets more or less flattened to a constant value, but the edges are having, where sharp changes are taking place, there are higher ripples here. This is known as Gibbs phenomena. We will come to that later on. So, if I take an infinite number of components, then only it will tend to, it will be ideally matching with a rectangular function. What would be the value of this at say 90 degrees? This is say omega naught t, that is theta. So, when omega naught t is pi by 2, what will be this value? What will be its magnitude tending to? Now, sine omega naught t at omega naught t equal to pi by 2, this will be sine pi by 2. So, the series will be tending to 1 plus minus 1/3 plus 1 by 5 minus 1 by 7. This is a convergent series. It will give you pi by 4. This sum is pi by 4. That means, if I have a magnitude of 1 here, the resultant will be coming to pi by 4. Approximately pi by 4 is approximately 80%, 0.8, very close to 0.8. So, if we normalize it by 4 by pi, if I multiply by 4 by pi, that height will be raised to if this is 1, then the first component will be here of magnitude 4 by pi. If this is of 1, then this will be of magnitude 4 by pi. Okay. If we have another example, I will take, if I have a function like this, Vt equal to sine omega naught t minus half sine 2 omega naught t plus 1/3 sine 3 omega naught t minus 1 by 4 sine 4 omega naught t, and so on. Okay. Now, for this type of function, I have added these even terms. Now, you will find if I take only the first term, it will be a pure sinusoid. If I take first and second term, you see what kind of distortion comes. It will be somewhat like this. Can you guess what it will tend to? Yes, it will come to a triangular shape. That is very good. If you take the third term, something like this. If you take the fifth term, there will be more variations. This will become sharper. So, this will tend to finally a function like this as we go to an infinite number of terms. Okay. So, basically what I wanted to drive at is, if you take so many harmonic terms, harmonic frequencies, then the overall function is again periodic with the same period. You take any combination of periodic functions and their harmonics, that means compared to the fundamental period, these periods are submultiples, okay, integral submultiples of this period. If you take any combination, the overall function will also be having the same period. Yes. So, Fourier series is Vt, as I had written earlier, we can write this as an cosine n omega naught t plus bn sine n omega naught t, n varying from 0 to infinity, okay, 1 to infinity, 0 is included here. All right. Now, the question is, what will be the values of these constants Ai's and Bi's? Now, to evaluate these, we take recourse to the properties that we discussed just now for orthogonal functions. Now, if Vt is this, if I integrate this both sides, if I integrate multiply by dt, what will be the result on the left hand side? You get over the period t. On the left hand side you get integral Vt dt over t. Here you get a0 into t, and all these orthogonal functions integrated over one time period will be giving you 0. We just now derived that. Okay. So, a0 comes out as 1 by t integral Vt dt. So, given function, if you integrate over one period and then take the average divided by the time period t, will give you a0. Okay. Next, Vt, if I multiply it by cosine m omega naught t dt and then take the integral over period t, what would be the result? So, on the right hand side you have got a0 into cosine m omega naught t dt plus sigma a m, okay, I will write ak cosine k omega naught t plus bk cosine sine k omega naught t into dt, okay, summated over k. Now, what will be this? This is a cosine function integrated over one period. So, it is an orthogonal function. So, this is 0. Now, cosine k omega naught t, I forgot to put cosine m omega naught t and then put dt, this multiplied by cos m omega naught. Now, in these products, when k is not equal to m, all other terms in this will become 0. Similarly, for this it will be 0. Only cosine m omega naught t that is present here will give me corresponding coefficient am. So, it will be am integral cosine squared m omega naught t dt, and that is what? That we have already evaluated as t by 2. So, am will be 2 by t integral Vt cosine m omega naught t dt. Okay. Similarly, you can also multiply by sine m omega naught t dt, integrate both sides, and you get Bm as 2 by t Vt integrated over t Vt sine m omega naught t dt. Okay. Now, we have made certain assumptions here. What are those assumptions? The assumption was, yes, it is a periodic function, all right, but the assumption was all these are integrable. There are definite values of integration. We have ruled out the possibility of a function going up to infinity, all right. So, the functions may have finite number of discontinuities, but the values must not go to infinity, number one. So, the integrals were assumed to exist. the integrals assumed to exist. That means they will exist, these integrals will exist provided these conditions are met. They are called Dirichlet conditions. Dirichlet conditions. That means Vt must be defined bounded in the range 0 to t, or you can say any t1 to t1 plus t, t1 to t1 plus t, that is over one period, and it will have a finite number of maxima and minima. Maxima and minima. Okay. They must have also first continuous first and second derivative, continuous first and second derivative, most of our functions obey these in most of the physical systems. If you have, for example, a periodic function having jumps like this, then at this point if I evaluate the value of the function from the Fourier series, so the limit of the Fourier series say at this point will be in the middle, that is half of these two extreme values. It will result in these values. So, these are the limits of the Fourier series. This is t and this is Vt. Okay. Ft is equal to A0 plus sigma an cosine n omega naught t plus Bn sin n omega naught t. All right. I can write this as Cn cosine n omega naught t plus theta n. All right, summated over n, where Cn will be nothing but an squared plus Bn squared, and theta n is equal to minus tan inverse Bn by An. Mind you, it is minus because in a cosine expression cosine A plus B becomes minus. So, Ft can be written, therefore, I can put this as C0 plus Cn cosine n omega naught t plus theta n summation. All right. What will be the values of Cn like? This may be C0, this may be C1, this may be C2, C3 and so on, normally progressively coming down, and correspondingly theta n For the first one there is no frequency, 0 frequency, that means something like your average value or DC value, it does not have a phase. Here it may be negative minus theta 1, I should not say minus theta 1 is in the negative direction, theta 2 may be in this side, theta 3 may be here, and so on. So, the representation of the Fourier series components in the time domain will look like this. For the function for which we have say evaluated C0, C1, etc., it will be this much C0 plus now I will write T. This is having C1 with a negative angle. So, it will be maybe like this, depending on the value of theta 1. It may be like this, of magnitude C1 plus this may be positive, this is of frequency twice that frequency C2, twice the frequency of C1, and so on. So, sum total of all these components at each and every point will give me the original periodic function, whatever be that. Okay. That function could have been maybe like this. We are not talking about any specific function here. Any periodic function whose components have been resolved is realized at every point by adding up all these values. Say at this point this plus this plus this and so on will give me at that corresponding interval this magnitude. Okay. Now, I have to match it with an infinite number of points here. That means, all these should be giving me the values at all these intervals. That means, there are infinite number of points where it is to be matched. So, there will be infinite number of components. To perfectly match this particular waveform, I need an infinite number of components. So, that is why Fourier series extends up to infinity. It may so happen a particular periodic function which may consist of 2 or 3 such functions, a regular function that we are discussing, say for example, this, it contains just first and third harmonic. But in general, any periodic function, especially when there are sharp changes, will contain a large number of harmonics, theoretically infinite number of harmonics. Okay. Next, let us take 1 or 2 examples. Suppose xt is a function which is given as a in this range and t by 2, t and t. That means, this is a kind of function. We define periodic functions only in one period, that is good enough. Like this. Okay. This is 0, t by 2, t, 3t by 2 and so on, this is minus t by 2 and so on. What will be the Fourier coefficients for such a function? Am will be 2 by t0 0 to, okay, we can write 0 to t by 2, a, this magnitude is a, into cosine m omega naught t dt, minus, sorry, plus t by 2 to t that this becomes minus a cosine m omega naught t dt. If you integrate 2a by t naught will come as a constant, and here you get sine of m omega naught t by m omega naught 0 to t by 2, then with a negative sign sine m omega naught t by m omega naught t by 2 to t. Then if you work it out with 2a by m into omega naught into t naught will give you 2 pi, is it not? Omega naught into t naught is 2 pi t, need not write t naught, t means that. So, this will be m into 2 pi, and inside the bracket it is sine m n omega m omega naught t, if I put t by 2, so sine of m pi, which will be always 0. So, both the limits will be giving me 0. So, all am's are 0, and bm it will be once again 2 by t naught, 2 by t minus cosine m omega naught t by m omega naught 0 to t by 2 plus minus of minus, there is minus a, and when you integrate you get another minus, so that gives me plus. Then there is an a, I can take that out, okay, cosine m omega naught t by m omega naught t by 2 to t. Now that gives me 2a by m pi correct me if I am wrong. Is this all right? 2a by m pi, 2 pi, m into 2 pi. Is it all right? Two. Check. Then sorry, 1 minus cos m pi, okay. Sorry. There is some slip somewhere, 2a by t, 2 by t naught, okay. So 2a by t naught, I should not have written t naught, anyway this was t, omega naught and t. Check it. Then this one is 2a by t cosine m omega naught t m omega naught. So you are putting t by 2. So m t by 2, that will give you pi, not 2 pi. Okay. And
it is a function of t.
Omega naught, or omega naught into t. Sorry, omega naught into t, not this t. So it will be 2. Okay. Okay. Omega naught into t is 2 pi.
And t naught will also be there.
Okay. So 2 a by m pi
t naught
into 1 minus cos m pi, all right. I have already put these two values, okay. So, that give me 1 minus cos m pi when m is odd,
Or so it will be 2. Then the total term
then it will be 2, and when m is even it is 0.
0.
There was some slip somewhere, anyway.
Yes, sir. The 2a by t naught, the t naught is not continuing afterwards in the second step.
2a by
T naught.
t, no, is this all right?
So there
2a by
t
m pi.
naught again, because after first term, first 2a by t naught is there.
2a by t,
After the t is not continuing afterwards.
no,
T
there
is
is no
there.
t here, there is no t here. So, t gets multiplied by omega naught, that has given me 2 pi,
Okay.
but this 2 should not have been there. Where is the fallacy? Oh, I understand. When you are adding this, there is a 2 coming out from here. You put m omega naught into t, omega naught into t by 2, so that gives you pi. So,
That is minus 1 plus 1.
so this is 1 minus cos m pi, again here 1 minus cos m pi. So, there is a 2 here, so that will get cancelled with this 2, okay. So, it will be 4, 2 into 2, 4 a by m pi, all right. There are actually 4 terms which are condensed in this. So, x t will be 4 a by pi sin omega naught t plus 1/3 sin 3 omega naught t plus 1 by 5 sin 5 omega naught t, and so on, okay. M is equal to 3, 5, etc., odd values. Because of the symmetry, it is the symmetry which causes some of the sine and cosine terms to vanish. They are not present because of the symmetry. Now, let us see some of the important properties of even and odd functions that we can use here. Any function f t we can resolve into an even part and an odd part, okay. Now, sum of even functions is equal to an even function, all right. Sum of odd functions is equal to an odd function, okay. Now, if f t, the given f t is even or odd, then how do I evaluate? See, f t I can write as f e t plus f naught t. Now, I want to evaluate a m. So, a m is 2 by t, okay, say minus t by 2 to plus t by 2, and instead of f t I will write f e t cosine m omega naught t dt plus again t by 2 f o t odd t cosine m omega naught t into dt. That is f t I have written in terms of these two components, all right. Now, this is an odd function, this is an even function. So, the product is an odd function. So, for an odd function, if you integrate from minus t by 2 to plus t by 2 between any minus t dashed to plus t dashed, it will be 0 for an odd function, is not. So, this term will be reducing to 0. Okay. So, what you are left with is even term. So, it will be 2 by t integral minus t by 2 to plus t by 2 f even part into cosine m omega naught t dt. All right. So, let us see first, if f t itself is even, then what happens? Then only a m will exist, is it not? The odd part cannot exist. That is, a m is equal to 2 by t minus t by 2 to plus t by 2, f t itself is f e t. So, f t into cosine m omega naught t dt. Now, for an odd function, for an even function, this product is even. For an even function, minus t by 2 to plus t by 2 is twice the integral between 0 to t by 2. So, I can write this as 4 by t 0 to t by 2 f t cosine m omega naught t dt, is it not? For any even function, even functions are like this. So, the total area, integral means total area, is same as twice this area.
Yes.
That is what I have done. Similarly, for an odd function, by the same logic, for an odd function, what will be the values? For an odd function, a's will be 0, only b's will be present, and the integral will be once again evaluated between 0 to t by 2 and multiplied by 2, f t sine m omega naught t into dt. Okay. Next, suppose we have half wave symmetry. What is half wave symmetry? If you have a function f t is equal to minus f t plus minus t by 2, that is, say a function like this, this is 0, this is t, this is t by 2. It is like a sawtooth wave, no, sawtooth function, alternately you twist the teeth, okay, you get a function of this kind. Now, what are the types of components that may be present in such a function? Let us see, let us multiply this function by a sinusoid. If I multiply this by a sinusoid, what will be the result? Okay, let me draw it a little more clearly. Similarly here, so this is one period, Okay. Now, if I multiply by a sinusoid, all right, and so on. Here the product is positive into positive, positive into positive, and so on. All right. Is it all right? Here
It will go positive.
so for odd terms I have taken a sinusoid sin omega naught t. So, this is an odd term, all right, B1 I have taken. Okay. So, if I take an odd function, the product is even, is it not? Here it is positive into positive, in this zone again it is positive into positive, all right. So, it is on this side also it is negative into negative is positive. So, it is basically the product is even.
Yes, sir.
Okay. So, for n odd the product is even, and hence the integral will have some finite value, non-zero value. Okay. So, these coefficients will exist and they are identical. So, you can take between 0 and t by 2, integral between 0 and 2. So, it will be 4 by t 0 to t by 2, that function f t and sin n omega naught t, where n is odd, and similarly this is Bn, and An will be similarly 4 by t 0 to t by 2 f t cosine n omega naught t. Okay. If you take n even, then what happens? Let us see. Now, you are having between here this and this point, say something like double harmonic. Here you see this is one period, this is positive and positive, but here it is negative and positive. This is negative, but this is a large value and this is this much value. Its counterpart is here, where both are negative. See, this component, the product of this part, this zone is equal in magnitude to the product of this, but here it is positive into negative, here it is negative into negative. So, they will be cancelling. So, this is an odd function. So, if n is even, product is odd, this product is odd, and hence the integral is 0. Okay. So, An and Bn will be 0 for n even for this type of half wave symmetric function. All right. So, thank you very much. In the next class we shall be continuing with this, a few more interesting features of Fourier series and some standard functions we will take for evaluating the Fourier series. Thank you. Good afternoon, friends. We are discussing last time Fourier series. Fourier series represents basically is a representation of a periodic function in terms of cosine and sine functions of different frequencies. The frequencies are multiples of one fundamental frequency. So, we wrote y t as a 0 plus summation a n cosine n omega naught t plus b n sine n omega naught t, where n varies from 1 to infinity. Now, this representation gives me the coefficients a n and b n including a 0 as 1 by t integration over t this function y t multiplied by the corresponding orthogonal function. Say if I want to evaluate a n, it is to be multiplied by cos n omega naught t. If it is b n, then to be multiplied by sin n omega naught t and then integrated over this period. And if it is a naught, then a naught is multiplied by just a constant. So, you have to just integrate this, and that gives me the coefficients a 0, a n and b n. We have used the properties of orthogonal functions. Now, one may express cosine n omega naught t and sin n omega naught t in terms of exponential functions. Similarly, sin n omega naught t as e to the power j n omega naught t minus e to the power minus j n omega naught t by 2 j. If we express the functions sine and cosine functions in terms of the exponential functions and substitute here, what we get is y t as a 0 plus a n for cosine n omega naught t.